Summation notation for mean and standard deviation. Summation notation in statistics many times are for large data sets. Also in statistics, there's need to add many terms together. For large data sets, one uses technology to add many terms together, but there needs to be a way to show to the reader that they want to add multiple values together. In mathematics, there's a symbol that means add the terms together. That symbol looks like the summation I equal 1 to n of x sub I. That means to add all the values all the x values together. It looks like this in symbols. The summation I equals 1 to n of x sub I is x1 plus x2 plus x3 plus keep adding up to get plus xn. An example is, let's write out the terms of this expression. The summation I equals 1 to 5 of xi. So the summation of I equals 1 to 5 of xi means that you can take x sub 1 plus x sub 2 plus x sub 3 plus x sub 4 plus x sub 5, and I stop because I hit 5. Note that sometimes this notation symbol is written differently, such as the summation I equal 1 to n with the I and n over here of x sub I, or sometimes just the summation x sub I. But they all mean add up all the terms. Summation notation is just adding terms together. The order of operations applies for these expressions. One of the places we see this is the formula for the mean. Consider the formula for the sample mean, which is x bar is equal to summation I equal 1 to n of x sub I all over n. This means to find the sample mean, add up all the values, then divide by the number of data values. Sometimes this formula is written without the indices on the summation. One just knows to add up all the data values. So we might write x bar is equal to summation of x all over n. Example, the following data set represents the weights of cats in pounds. Find the mean. So we have the set 6.8, 8.2, 7.5, 9.4, and 8.2. Find the mean weights of the cats. Notice in this data set there are 5 weights, so n equals 5. The formula for the mean in this case would be x bar equals the summation of the x's over 5. This means add up all the weights first and then divide by 5. So that means we're going to take x bar would equal 6.8 plus 8.2 plus 7.5 plus 9.4 plus 8.2, and then we're going to divide that all by 5. Gives me 401 divided by, 440.1, sorry, divided by 5, which is 8.02 pounds. The formula for the standard deviation, the formula for the simple sample standard deviation is S is equal to the square root of the summation I equal 1 to n of x minus x bar quantity squared over n minus 1. This formula looks complicated, but if you use the order of operations, you can see that you do inside parentheses first, then square each of those answers, then add all those answers together, then subtract n minus 1, then divide those two numbers, and lastly, take the square root of the number you have. This is actually easier to perform in a table format. Also, to make this formula a little easier to read, you may see this formula written without the notation of the indices on the summation symbol. It is just assumed the summation symbol means add up all the values. So you'd see S is equal to the square root of the summation x minus x bar quantity squared over n minus 1. Example, the following data set represents the weights of cats in pounds. So we have the data set 6.8, 8.2, 7.5, 9.4, and 8.2. Find the sample standard deviation. This is easier to do in a table, so one doesn't get lost in the formula. The first thing to compute in the formula is x minus x bar, so start with a column of the x data values, which we call x, and then a column of x minus x bar. Notice the mean, or remember the mean, is 8.02 pounds. So we have 6.8, and we'll take 6.8 minus 8.02 equals negative 1.22. 8.2 minus 8.02 gives me 0.18. 7.5 minus 8.02 equals negative 0.52. 9.4 minus 8.02 is equal to 1.38. And then 8.2 minus 8.02 is 0.18. Now the next thing to do in the formula is to square each of these numbers. Remember, the squaring means multiplying a number by itself. In your calculator, you will need to put parentheses around the number in order to square the negative sign. Again, add the column to compute these numbers. So we added a column of x minus x bar quantity squared. We have our x's of 6.8, 8.2, 7.5, 9.4, and 8.2. Then we have our x minus x bar column of negative 1.22, 0.18, negative 0.52, 1.38, and 0.18. Now we will square each of those numbers. So we're going to take negative 1.22, and we're going to square it. Notice I put in parentheses, and I get 1.4884. We're going to then take 0.18. We're going to square it. Again, I put in parentheses just to remind myself to put parentheses in. That gives me 0.0324. Parentheses negative 0.52, close parentheses square, gives me 0.2704. Parentheses 1.38, close parentheses squared, gives me 1.9044. And parentheses 0.18, close parentheses squared, is 0.0324. Now the formula says add up all these numbers. So now we're going to take each of these numbers, the 1.4884 plus the 0.0324 plus the 0.2704 plus the 1.9044 plus the 0.0324. Add them all together, because that's what the formula says to do next, is the summation of x minus x bar quantity squared. Add all those numbers together, gives me 3.728. Next, you want to find n minus 1. N, remember, was 5, so that's going to be 5 minus 1, or 4. So if we look at our formula, again, in our formula, we're going to take the sum of 3.728 and divide by that 4. And that gives me 0.932. Finally, you're going to take the square root of that final answer, 0.932, and you get approximately 0.932. So the standard deviation of cat's weights is approximately 0.932. Oh, sorry, I wrote 932, but I apologize, I wrote the wrong answer. Give me a second. The square root of 0.932 is 0.965. There we go. So the standard deviation of cat's weights is approximately 0.965 pounds.